Organic molecules are molecules that are made up largely of carbon, but can also contain various other molecules and types of bonds. The reason why carbon is the fundamental basis for organic chemistry and organic molecules is because we say that carbon is tetravalent. Tetravalent refers to its valency, saying that it has 4 valence electrons and as a result is able to form 4 bonds. What makes that unique is that carbon is now able to bond with itself and form longer chains, and we call that ability carbon's ability to catenate, the ability to form long chains by bonding with oneself. And so what this does is it creates a problem in that molecules can no longer be completely defined by the traditional molecular formula. If we use a simple example, a molecule C5H12, a molecule that contains 5 carbons and 12 hydrogens, we do not know from looking at that molecular formula what the structural arrangement is, which is why it now becomes necessary for us to have a structural formula. The structural formula can show the way in which those carbon atoms are arranged with each other. The first possible arrangement here being 5 carbons arranged in a straight chain. Then there are also 2 other possible arrangements, those being 4 carbons with a single branch coming off one of the carbons, and also then 3 carbons in a chain with 2 branches coming off those carbons. As we can see here, these 3 molecules are all defined by the molecular formula C5H12, but they are completely different, which is why structural formula becomes important. And it's important to remember in structural formula that all the necessary hydrogen atoms must be drawn in. A slightly simplified version of structural formula is called condensed structural formula, where each carbon is defined by, or is shown with the number of hydrogens or various other atoms attached to it. So we say this carbon here has 3 hydrogen, this one has 2, 2, 2, and then the final carbon being CH3. The last way that we can define these molecules is called the IUPAC name. It is the International Convention for Naming Organic Molecules. And the IUPAC name can be broken down in a number of ways, but essentially what we can do if we decide to name this molecule over here, we can say this molecule has a 4-chain carbon, or 4 carbons in its longest chain, which tells us that this must get the prefix but. We can also see that there are only single bonds, which means it belongs to the homologous series called alkanes, and as a result gets the suffix ane, so this is butane. And then finally we can see that there is a branch coming off here of a single carbon, that meaning that there is a methyl group. Methyl, the YL, represents the fact that it's a branch, and we need to specify that that is on the second carbon. So the IUPAC name is very useful because different parts of that name tell us everything about the molecule. The root of that chain we know is a 4-carbon chain. We can see that it is an alkane, which means that it consists of only single bonds from the suffix. We can see that there is a branch represented by the YL, and we can also see that that branch is a single carbon long and is attached to the second carbon in that chain. So in conclusion, organic molecules are molecules made up of carbon that catenates to form long chains. The chains are defined by the number of carbons, where a chain containing 1 carbon gets the prefix meth, and here we can see the prefixes meth, eth, prop, but, pent, hex, hept, oct. We would typically deal with chains up to 8 carbons long. We then get something called a functional group that defines the type of molecule, and then we also get branches that can be attached to that main chain. There are 4 ways in which we can express a molecule: molecular formula, structural formula, condensed structural formula, and the IUPAC name. It is important to understand the difference between a functional group and a homologous series when looking at organic molecules. A functional group is a bond atom or group of atoms that determines the physical and chemical properties of a group. of organic compounds. That group that is referred to is the homologous series, where a homologous series is a series of organic compounds that have the same functional group and can be described by the same general formula. So what this tells us is that the functional group is that bond atom or group of atoms that defines a molecule. So the simplest molecule that we find has a functional group that is a carbon-carbon single bond, and we say that the functional group is the carbon-carbon single bond, and the homologous series is the alkane. The general formula tells us that it is always CnH2n plus 2, which tells us that if you have a compound that has 5 carbons, then it would have 2 times 5 plus 2, that being 12 hydrogens, and alkanes always get the suffix ane. Similarly, a compound that contains a double bond is called an alkene and has the general formula CnH2n, which tells us that if it contains only one double bond, then it has 4 carbons, then it would have 8 hydrogens, and that would always get the suffix ene. A triple bond is the third type of functional group, and that is defined by the formula CnH2n minus 2, which says that if we had a compound that had 6 carbons, it would then have 10 hydrogens present, and it gets the suffix yne. That is the alkanes, alkenes, and alkynes. Then we get haloalkanes, that where one of the hydrogens is replaced by a halogen, the halogens being fluorine, chlorine, bromine, and iodine. And in that case, our general formula then, if we took the original alkane, would be C5H11, because one of the hydrogens has been replaced, where X represents any one of the halogens, in this example, bromine. The next type of functional group is known as the hydroxyl group, that is an oxygen single bonded to a hydrogen. And any compound that contains this hydroxyl group would belong to the homologous series of the alcohols and would therefore get a suffix anol. In condensed structural formula, that is represented by an OH. Next, we have what is known as the formyl functional group, which is a carbon double bonded to an oxygen and single bonded to a hydrogen. And any compound that contains this formyl functional group would belong to the aldehyde homologous series and therefore get the suffix anal. It is represented as CHO in condensed structural formula. Very similar to the aldehydes or the ketones, where we have the carbonyl functional group, which is a carbon that is double bonded to an oxygen, but can form 2 chains, one on either side of that carbon atom that is bonded to the oxygen. Any compound that contains a carbonyl functional group is then a ketone, and this is represented with a C with an O in brackets, and it gets the suffix anone. Then we get the carboxyl functional group, which, as we can see, is a combination of the hydroxyl group and the carbonyl group, where we have a carbon double bonded to an oxygen, also single bonded to an oxygen, which is single bonded to a hydrogen. Any compound that contains this carboxyl functional group is a carboxylic acid, represented in condensed structural formula as COOH, and gets the suffix anoic acid. Finally, the last functional group that is dealt with in NSC is the ester functional group, a carbon single bonded to an oxygen and double bonded to an oxygen, where you have 2 chains, one going off on either side of that. This is known as the ester group, and it belongs to the ester homologous series, represented by a COO, and this, because there are 2 chains, gets one of the chains gets the suffix YL, the other gets the suffix anoate. It is important to understand these functional groups, because once you understand what each functional group represents, you can immediately identify what homologous series that compound belongs to. Important to note here that any compound that contains the hydroxyl functional group, no matter how long that carbon chain is, belongs to the alcohol homologous series. Alkanes are the simplest organic compounds, as they contain only carbon-carbon single bonds and carbon-hydrogen bonds. any substance that is identified to be an alkane will get the suffix ane and be described by the general formula CnH2n plus 2. So the way that we would name an alkane is you start by identifying the longest chain in the molecule, and here we can see that the longest chain in this molecule is made up of 3 carbons. The prefix for a compound containing 3 carbons is prop, and because we can now see that this compound contains only carbon-carbon single bonds and carbon-hydrogen single bonds, we know that it is an alkane and therefore gets the suffix ane. So this compound is therefore named propane. We can see here that this compound contains 3 carbons and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and therefore abides by the formula CnH2n plus 2. We can also draw this in condensed structural formula as CH3, CH2, CH3. We can do the same for this compound here, once again identifying the longest carbon chain, where we can see that there are 6 carbons. The fact that there is a bend in the chain does not affect this, so we can see that there are 5 carbons in this longest chain, which means that it gets the prefix pent. We can then see, since there are only carbon-carbon single bonds and carbon-hydrogen bonds, it is an alkane, therefore gets the suffix ane. And we can see that this is made up of 5 carbons and 12 hydrogens, and the condensed structural formula for this would be CH3, CH2, 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 CH3. This can sometimes be written as well as CH3 followed by 3 CH2. So by putting it in brackets here, we are abbreviating it, and then followed at the end by a CH3. It's important to note here that we say that alkanes are saturated because each carbon has the maximum number of bonds with different atoms, or we say it contains only single bonds. Alkenes are compounds that contain at least one carbon-carbon double bond, where we know that a carbon-carbon double bond is one in which each carbon present in the bond shares 2 electrons. Alkenes therefore get the suffix ene, and they have the general formula CnH2n. So we would name an alkene by identifying the longest chain containing that double bond, which in this case we can see is 4 carbons. We know that 4 carbons gets the prefix bute. And now, because we know that this is an alkene, since it contains a double bond, we would call it butene. But we need to indicate the position of that double bond, and we always number so that the double bond, or that functional group, has the smallest number possible, which means that this would be carbon number 1, and we would call this but1ene. We would, for a more complicated molecule, follow a very similar pattern, where we first identify the longest carbon chain, keeping in mind that bends in the chain do not affect the chain length, where we can see that the longest chain here is 1, 2, 3, 4, 5, 6, 7 carbons long, which means that we get the prefix hept. We can see once again that it contains a double bond, this time 2 double bonds, but therefore gets the suffix ene, but we indicate that there are multiple functional groups with a prefix di, tri, or tetra, so this would now be diene. And finally, we must number this, we must indicate the position of those double bonds, and we again choose to number from the side that makes those numbers as small as possible, so we would call this hept 1, 4, di, saying that there are 2 ene, 2 double bonds, and that would be how we name this alkene. We would, in condensed structural formula, we follow exactly the same pattern. This would be CH3, CH2, CH, followed by CH2. It would be up to the person reading this to see that each of these 2 carbons is 1 bond short, and therefore see that there is a double bond present there. And the same pattern here, where we say that this is CH3, CH, followed by a CH again. We can see that each of those carbons is one bond short, followed by once again a CH, CH, and then CH2, and then CH3. We say that alkenes are unsaturated compounds because they contain a double bond. And once again, it is important when there are multiple double bonds, we would indicate that with di for 2, tri for 3, and tetra for 4. Alkynes are organic compounds that contain at least one carbon-carbon triple bond. We remember that a triple bond refers to a bond between, in this case, two carbon atoms where each atom donates 3 electrons, and as a result 3 bonds are formed between those atoms. Alkynes get the suffix YNE and have the general formula CnH2n-2. We would name an alkyne by counting the number of carbons in the longest chain. In this case, this chain has 3 carbons. 3 carbons we know gets the prefix prop. And we know that it should get the suffix YNE, but we need to indicate the position of that triple bond, and we always count from the side that makes that triple bond on the smallest number carbon possible, so this would be called prop 1 ine. The condensed structural formula for this molecule would then be written as CH3C CH, and then the reader would be required to see that a triple bond is necessary to ensure that each carbon has formed 3 bonds. The next one, we would follow the same pattern where we count the number of carbons in the longest chain, where a bend in the chain does not affect the chain length. So 1, 2, 3, 4, 5, 6, 7, 8. So we know that this gets the prefix oct. We can see that there are 3 triple bonds present, which means that this is going to be a tri-ine, and we indicate the position of those 3 double bonds by seeing that they are on the 1st, 4th, and 6th carbon. So we say oct 1, 4, 6, tri-ine. And the condensed structural formula for this molecule can be written as CH3 followed by a C followed by another C, 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 CH2, C, CH. And our final example here, we can see that there is a triple bond and a double bond present, which would suggest that this is both an alkyne and an alkene, but the alkyne takes preference over the alkene, so we follow the same numbering pattern. 1, 2, 3, 4. This is a bute molecule. And what we do to indicate that there is a double and a triple bond is we say that this is bute 3N1 ine, where we always number so that the main functional group, in this case the triple bond, has the smallest possible number, which is why we have numbered from the left, and we always show that there is the alkene first and the main functional group comes last. This type of question, a question in which there are 2 different functional groups, would not appear in the NSC syllabus, but this is just for interest's sake how you would answer a question like this. We can then see that each of these alkynes subscribes to the general formula CnH2n-2 by looking at prop 1 ine, seeing that that contains 3 carbons and 1, 2, 3, 4 hydrogens, C3H4, and this molecule over here would not necessarily subscribe to this formula because this formula applies when there is only 1 triple bond, and here there are 3 triple bonds, so this general formula only applies in cases where there is 1 triple bond present. And finally, it is important to remember that a compound that contains a double or a triple bond or a multiple bond is said to be unsaturated. It is only the alkanes that are saturated compounds. Alkyl halides are seen as branches of organic compounds where at least one hydrogen has been replaced by a halogen, the halogens being fluorine, chlorine, bromine, and iodine. since these are seen as branches, they are added to the name of the compound by use of a prefix. And so we would still name the carbon chain in exactly the same way, and we show that with this example here where we have 4 carbons in the main chain, therefore it gets the prefix but, and it is an alkane since there are only single bonds, so it is therefore butane. But now as we can see that by numbering from the right hand side, there is a fluorine in place of a hydrogen on the second carbon, so we would therefore name this fluorobutane, and again the position is important, so we call it 2-fluorobutane. This can now be applied to any organic compound that includes alkynes. So here we can once again follow the same pattern where we can see that this is an alkyne as a result of this triple bond. This triple bond tells us it gets the suffix YNE. We can see that the main chain has 5 carbons in it and therefore gets the prefix pent, and it is important to indicate the position of that triple bond, and that is on the first carbon, so pent 1 ine. And we can now see that there are 4 alkyl halide branches here, those being a fluorine, a chlorine, and 2 iodines. And since we have started numbering with this as carbon number 1, we must continue doing that in naming the entire compound: 4-chloro, 3-fluoro, 5,5 diiodo-pent 1 ine. A couple of things to note with this name. Firstly, the alkyne, the triple bond functional group, takes preference over all of the others, which is why we always number from the side that gives that the smallest positional number. The second thing is that we arrange these prefixes, these branches, alphabetically, where we can see that C comes before F, which comes before I. It is important to remember to ignore the prefix di, tri, or tetra. We are only comparing the first letter of iodo, fluoro, and chloro. And once we have chosen to number from the left-hand side for our alkyne, we must keep that numbering, which is why this is carbon number 3, carbon number 4, and carbon number 5. And it is important to identify that both iodines are on the 5th carbon, 5,5. It is not acceptable to leave this as simply 5-diodo-pent 1 ine. Organic compounds are often found to have branches, or what we call alkyl groups, that are attached to the main carbon chain. And there is a naming convention for how we name those branches, or once again alkyl groups. Our first step remains the same, and that is to identify the longest carbon chain possible in that molecule. So for this example over here, our longest carbon chain is 1, 2, 3, 4 carbons, which means that it gets the prefix but. We can see that it contains only single bonds and therefore is an alkane and gets the suffix ane, butane. And now what we can see is that there is a single carbon that is attached to that main chain. And so that single carbon gets the same prefix that a single carbon chain would get, but now because it is a branch, it gets the suffix YL. So this would then be called methyl butane, and that is all one word. What is once again important is to indicate the position of that branch, and we always count from the side that makes that number as small as possible. So if this is carbon number 1, then this would be 2-methyl butane. The same principle can be applied to longer molecules and multiple chains, where our first step once again is going to be to identify the longest carbon chain, where here we can see that our longest carbon chain is made up of 6 carbons. Note here that this branch at the end is not a branch because it is on the first or on the last carbon, and as a result forms a continuous chain that is 6 carbons long. We know that 6 carbons gets the prefix hex, and since it is an alkane with only single bonds, we would call that hexane. Then what we can see is there are 2 separate branches. One branch that has only a single carbon, that we would know is a methyl group, and another branch that has 2 carbons, which makes it an ethyl group. These groups must always be arranged alphabetically, so we can see here that alphabetically the ethyl group comes before the methyl group, and we must number them as 2-methyl, 3-ethyl, and so the IUPAC name for this compound is then 3-ethyl 2-methyl hexane. That is all one word. We can do the same thing where we remember that the halogen branches are also considered branches and are therefore of equal importance. So once again, we identify our longest carbon chain, that here is 7 carbons, and therefore we are dealing with a heptane molecule, where we can now see that we have 2 methyl branches, a fluoro branch, and an ethyl branch. And once again, we arrange these alphabetically. Alphabetically, the ethyl branch would come first, and that would be a 4-ethyl because it is on the 4th carbon. There are 2 methyl branches, both of those on the 2nd carbon. And just like we did for the halogens, when there are 2 of them, we would use the prefix di. So we are going to have dimethyl here, and then a fluoro branch on the 3rd carbon, which makes the IUPAC name for this molecule 4-ethyl 3-fluoro 2,2 dimethyl heptane. Important to note here that even though they are both on the 2nd carbon, it is still necessary to list the number 2 twice and to indicate that with a di. Another important thing to note is that we still, when arranging them alphabetically, we still look at the M in methyl. We do not think that this is a D which should come before E. We always look at the prefix that is a result of the number of carbons in that chain. The last thing to note here is that in the condensed structural formula, branches are written in brackets. So this molecule here would be CH3 followed by a CH followed by a CH3 branch, which is in brackets, followed by another carbon that is attached to a single hydrogen, followed by a branch that is a CH2 molecule, followed by a CH3, and then a CH2 molecule, another CH2 molecule, and a CH3 to end that. So branches in condensed structural formula are written in brackets. Alcohols are the homologous series of molecules that contain what is called a hydroxyl functional group, and the hydroxyl functional group is a carbon that is single bonded to an oxygen that is in turn single bonded to a hydrogen. We always draw it at this angle because the oxygen atom has 2 lone pairs of electrons that repel the hydrogen atom into that curved or bent configuration. So any compound that contains this hydroxyl group, the functional group of the alcohols, is said to be an alcohol and therefore gets the suffix -anol. The rules for how we name compounds remain very similar from there onwards, where we would name this compound here first by identifying the longest carbon chain, which is 3 carbons, and 3 carbons we know gets the prefix prop. And now that we know that it is an alcohol because it has this hydroxyl functional group, we know it should be propanol, but it is important to indicate the position of that hydroxyl group, so we would call this propan-2-ol, which says prop tells us that it is a 3 carbon chain, anol tells us that it is an alcohol, and the 2 tells us that the hydroxyl group is on the 2nd carbon. The other rules still apply, as we would have in branches, where here we can see we once again have an alcohol because it has the hydroxyl functional group, and we start by identifying the longest possible carbon chain. In this case, that is meth, eth, prop, bute, pent. We can see that it is an alcohol, so it should be pentanol, but the change now is that there are 2 hydroxyl groups, so we would write this as pent 2,3-diol. We use the same prefixes for multiple functional groups as we had di, tri, and tetra, so this would be pent 2,3-diol, with this being carbon number 1. and then we can see that there are 2 methyl branches both on the 4th carbon, and so the complete IUPAC name for this molecule would be 4,4-dimethyl pentan 2,3-diol, and that is all one word. Important to note here that we always number an alcohol so that the hydroxyl groups are the smallest possible numbers. So we know that technically by numbering this as carbon number 1, the total number would have been smaller, but we have to number from the side closest to the hydroxyl functional group when it is an alcohol. Another important concept to understand in alcohols is that of primary, secondary, and tertiary alcohols. And we can illustrate that here by seeing that the carbon to which the hydroxyl group is bonded in this molecule here is in turn only attached to one other carbon, and as a result we call it a primary alcohol. So because the carbon to which the hydroxyl group is attached is only attached to one other carbon, we call it a primary alcohol. We can then see in this molecule here that since this carbon to which the hydroxyl group is attached to 2 other carbon atoms, we call it a secondary alcohol. And then finally, in this example here, the carbon to which the hydroxyl group is attached to 3 other carbon atoms, and as a result we call it a tertiary alcohol. This becomes important in the next section where we start looking at how alcohols react with each other. So it is important to be able to identify primary, secondary, and tertiary alcohols, and that is done by looking at the number of carbons to which the carbon attached to the hydroxyl group is attached. Aldehydes are organic compounds that contain a 4-mile functional group. The 4-mile functional group is a carbon that is double bonded to an oxygen and single bonded to a hydrogen, and then single bonded to the rest of a carbon chain. Now, any compound that contains this 4-mile group is called an aldehyde and therefore gets the suffix -anal. Now, what we can see, what is unique about this 4-mile group is that since it only allows the carbon chain to extend in one direction, we do not need to indicate the position of that 4-mile functional group. So we would name a compound by counting the number of carbons in the longest chain, in this case meth, eth, prop, bute. And we would then say that since it contains this 4-mile functional group, it is an aldehyde and therefore gets the suffix -anal, and so we would call this butanol. It is unnecessary to call it butan 1-al because aldehydes with a 4-mile group are always on the first carbon. We can see this with a slightly more complicated molecule, where here we identify once again our longest carbon chain. It was also possible to identify this as the longest chain, but what that would then do is create a branch that has a branch off it, and that is unnecessarily complicated for us, so we choose the longest carbon chain possible. We therefore see that this is 5 carbons and therefore pent. We can see that it contains the 4-mile group and therefore must be pentanal. And then what we do is, in the same way as we always would, we name the alkyl branches. Here we can see that there are 3 carbons attached to the main chain. Note here that the fact that it bends does not affect the way in which we name it. It is still 3 carbons. 3 carbons gets the prefix prop, and propyl because it is a branch, and here we have a methyl branch. And now because this is an aldehyde, this is automatically carbon number 1, and as a result the propyl branch must be on carbon number 2 and the methyl branch on carbon number 3, and so alphabetically we would call this 3-methyl 2-propyl pentanol. Once again, this is all one word. Ketones are compounds that contain what is called a carbonyl functional group, which is very similar to the 4-mile functional group of aldehydes, the difference being that the carbonyl functional group allows for the carbon chain to extend on either side of it, where we have a carbon double bonded to an oxygen, but carbons can be attached on either side of that carbonyl group. Any compound that contains this carbonyl group is called a ketone and gets the suffix anone, and the same naming conventions apply, where we start by identifying the longest chain that contains that functional group. In this case, that is 5 carbons, and therefore this is pent, and it would be pentanone, but it is important to indicate the position of that carbonyl group, and we can see that this is on the second carbon. We need to count from the side that makes that number the smallest, so we call this pentan to one. It is important to keep in mind that when this carbon double bonds to an oxygen, it already has 4 bonds, so it is not necessary to draw another hydrogen on. We can then do a slightly more complicated example, where here we start once again by identifying the longest carbon chain that contains that functional group. Again, do not be confused by a bend in that chain. The longest chain here, meth, eth, prop, but, pent, hex, hept. So we know that this is going to be heptanone, but it is important once again to number from the side that makes this the smallest number. So we are going to call this heptan 3 one, and then identify 1 methyl branch and 2 fluoro branches. Alphabetically, the fluoro branches should be placed first, and those fluoro branches are both on the 5th carbon, so we call this 5,5 difluoro, di to indicate the fact that there are 2 fluorines attached both on the 5th carbon, and 6 methyl heptan 3 one. It is important to see here that this is very similar to an aldehyde, but you would never have a pentan 1 one, because if it was 1 one, that would mean that the carbonyl group is on the 1st carbon, which would make it an aldehyde. So a ketone will never have a 1 in it, because if it had a 1, it would then be an aldehyde, because aldehydes have the formyl group placed on the 1st carbon. Carboxylic acids are organic compounds that contain what is called the carboxyl group. The carboxyl group is a carbon that is double bonded to an oxygen and single bonded to an oxygen, which is in turn bonded to a hydrogen, which, as you can see, looks a lot like the carbonyl group and hydroxyl group that are attached together, which is where the name comes from. Any compound that contains this carboxyl group is called a carboxylic acid and gets the suffix anoic acid. So we would name this compound here by identifying our longest carbon chain as having 2 carbons, therefore eth, and with this carboxyl functional group, we say it must be a carboxylic acid and is therefore ethanoic acid. And now, for the first time in organic chemistry, we are naming something with 2 separate words, ethanoic and acid, with a space between those words. The naming conventions remain the same for molecules that include branches. Here we can see the longest carbon chain is 3 carbons, that being prop, and as a result we would call this propanoic acid, since it has a carboxyl group attached to it. Again, that is written as 2 words. And then we would see that once again the carboxyl group must always be on carbon number 1, which means that this methyl branch is on the 2nd carbon, and we would call this 2-methyl propanoic acid. Esters are organic compounds that contain the ester group, which is a carbon that is double bonded to an oxygen and also single bonded to an oxygen, with 2 separate carbon chains that go off in separate directions. When a compound contains this ester group, it is said to be an ester and gets the suffix in 2 words, YL and anoate. And it's important to be able to identify which part gets which suffix. So the first thing that you need to do is identify the ester functional group when naming a molecule, and here we can see that we have the ester functional group. We can see that this is broken up into 2 parts. There's one part of this molecule that is attached only by a single bond to the oxygen. That is always seen as the branch to this ester, and as a result comes first and gets the suffix YL. So in this case, that is 2 carbons, meth-eth. So we would call this ethyl. This is also 2 words, and the second part of this compound is 3 carbons attached to that ester group, which ends in that carbon-oxygen double bond, and that 3 carbons gets the prefix prop and suffix NO8. Once again, as a result of the structure of this, it is not necessary to name where this takes place or give a number. We can do that with one more example. We first identify the ester functional group, and then we identify the part of that functional group that is attached by a single bond to the oxygen. In this case, we can see that that is a 5-carbon chain, which means that the part that gets the suffix YL is meth, eth, prop, but, pent. So we would call this pentyl. And then the part of this compound that is attached to the double bonded oxygen is always the main part, and that gets the suffix NO8, meth, eth, prop, but. So this would then be correctly called pentyl butanoate.